Good day, everyone. For this module, we will be tackling on how stress affects the chemical undergoing reactions. Basically, this will all be about understanding the equilibrium chemistry and the Le Chatelier's principle. So I am here to discuss the first part of this module, which will be about the concept of equilibrium and the equilibrium constant. Chemical equilibrium is achieved when the rates of forward and reverse reactions are equal and the concentrations of reactants and products remain constant. Let's say, for example, we introduce some N2O4 into a sealed flask and kept it in 200 degrees Celsius. We can see that a change occurs immediately. The colorless N2O4 gas begins to turn into a pale brown color, indicating that some of N2 and O2 gases have already been formed. And as the time passes, the color darkens, and after a few moments, the color stops changing as shown here in picture C and D. Although it turned brown, we couldn't say that this container contains fully of NO2 gases. Since this is a reversible reaction, some of the NO2 gases are still transformed back into N2O4 gas. If we will be visualizing this using graphs, this shows that at a certain time, which was the picture C and D, where the rates of the forward and reverse reactions are finally equal. On the other hand, we could see in this graph that we started initially with a high concentration of the reactant, which is the N2O4, and there are still no products formed at the initial phase. But as the container was placed from a lower temperature into a place where there is 200 degrees Celsius, the equilibrium has changed, and by the time it reached the new equilibrium, it becomes favorable to the formation of products. Although we have more products formed by the time we reach the new equilibrium, take note that in equilibrium we are concerned if the concentrations of all reactant species remains constant. There are two types of equilibrium reaction: the homogeneous equilibria, which contains the same phase for all reacting species. For example, we have this reaction between acetic acid and water. Though we have this distinction that there is a liquid phase here, we all know that the water exists in a liquid phase. As we review, the aqueous solution is a special type of liquid formed by dissolving a compound in water, so it is still considered a liquid phase. Thus, we will still have a homogeneous equilibria all throughout this reaction. On the other hand, the heterogeneous equilibria is a reaction involving reactants and products that are in different phases. We have the sample here of reaction of solid calcium carbonate, in which it yields solid calcium oxide and carbon dioxide gas. And since this is a reversible reaction, the products can react to each other to form the calcium carbonate again. So we could actually know what is specifically happening at the reactants and products at a certain equilibrium by using equilibrium constants. The equilibrium constant of a chemical reaction is usually denoted by the symbol K, and using K, we'll be able to identify if there are more products and or more reactants at equilibrium. There may be two types on how we could express equilibrium constants. One is the equilibrium constant in terms of concentration. This equilibrium constant is used for both homogeneous and heterogeneous reactions. Second is the equilibrium constant in terms of pressure. Take note that this equilibrium constant is only applicable for and limited to gas reactions. So we have this simulation here from Bozeman Science, which shows how reversible reactions work. On the right is the K meter, which is going to measure the K value. So this is going to be, K is going to be the number of products divided by the reactants. On the right, you could see that we have thermometer, and you could observe later that the equilibrium constant varies at different temperatures. For now, we could see that if we have the same level of concentration on both sides, our K value is equal to 1. Now, as we have more concentration in the product side, thus our numerator will become larger and our K value will be larger than 1. But if we have more concentration on the reactant side, our denominator will become larger, and thus our K value will become less than 1. But this model oversimplifies a little bit because we only have products and reactants in this simulation. And so if we got a reversible reaction like this where this represents the reactants and this represents our products, we cannot use this simplified equation for K. But if we were to figure out for a more complex kind of an equation, this is the general way that we write out K, where K represents the concentration of one of our products. So that is going to be C raised to the power of the number of moles that we have on that chemical, multiplied to the concentration of the another product, which is D, raised to the power of the moles of this product as well. Likewise, we're going to put the reactants on the bottom. It's also simply the concentration raised to its corresponding number of moles. So we're going to use this equation when dealing with finding concentration or pressures and equilibrium. So now we will be practicing on how to write equilibrium constants for homogeneous equilibria. Take note that when we're writing equilibrium constant concentrations, we can exclude the liquid since in thermodynamics, the activity of pure liquids will only be equal to 1 and thus it will not affect when we are computing for equilibrium constants. For letter A, we could write equilibrium constant in terms of concentration and thus Tc is equal to the product of the concentration of the product side all over the reactant, which is the HF, and you can see that we already excluded here the liquid. So for letter B, we could see that this is a gas reaction, and thus we can express its equilibrium constant in terms of concentration and pressure. For Kc, it will be equal to the concentration of the products raised to its mole all over the product of the reactants raised to their corresponding moles. For Kp, it will be the pressure of the product raised to its corresponding number of moles all over the product of the reactants raised to their corresponding number of moles. For letter C, it is just the same as the letter A. So you could already try this on your own. So for heterogeneous equilibria, aside from liquids, take note that we may also exclude writing solids when writing equilibrium constant concentration since the activity of pure solid will also only be equal to 1. Thus, the solids will have no effect on the equilibrium. So for letter A, it is a gas reaction. Thus, we can express its equilibrium constant in terms of concentration and pressure. For Kc, it will be just the product of the concentration of the products since our reactants is already a solid and it's the same with the Kp. Only the pressure of the products are computed. Same for the letter B. Only the concentrations of the product will be included in the equilibrium constant expression. And for letter C, we could see that this is a gas reaction since we have a solid in the reactant side and the product will be liquid. And the activity of pure solid liquid is only equal to 1. So thus this is a gas reaction and we can express its equilibrium constants in terms of concentration and pressure. Thus the Kc will be equal to 1 since this is a pure liquid all over the concentration of the gas raised to its corresponding mole. And same for the Kp, activity of the pure liquid from here will be 1 all over the pressure of the gas raised to its corresponding number of moles. So how do we convert Kc into Kp? We'll basically use this equation wherein Kp is equal to the equilibrium constant in terms of concentration, which is 9.60, times the ideal gas constant, which is 0.08206, times the temperature in Kelvin, which will be 573, raised to the change of N, and change of N is equal to the number of the moles of the product minus number of moles of the reactant. So that will be 2 minus 4, and our change in moles will be -2. And this will be raised to -2. And thus our Kp is equal to 4.34 times 10 raised to -3. So in summary for the part 1, we were able to define the chemical equilibrium and how it relates to reaction rates. We were also able to write equilibrium constant expression for any reaction and also relate the equilibrium constant in terms of concentration and the equilibrium constant in terms of pressure for gas reaction.
Now, moving on, I'm John Martesero, and I'm here to discuss the second part of the module, which is understanding and working with equilibrium constants. So just to give you a recap about chemical equilibrium, this occurs in a reversible reaction when the forward and reverse reactions proceed at the same or equal rate, hence the term equilibrium. This results in constant concentrations of the reactants and products over time. And so in other words, during or at equilibrium, the rates of the forward and the reverse reactions are equal, and so there is no net change in the concentrations of both of them. And in relation to equilibrium constants are crucial in determining the direction and extent of chemical reactions at equilibrium. So this equilibrium constant, denoted as the letter K, quantifies the ratio of the product concentrations to the reactant concentrations at equilibrium. As we can see here, it may be expressed as Kc for the ratio of concentrations, but it may also be expressed as Kp for ratio of partial pressures. The expression of the equilibrium constant for a genuine reaction is shown here, where the small letters A, B, C, and D are the stoichiometry coefficients. As we can see, The expression for the equilibrium constant K involves multiplying the concentrations of the products, each raised to their respective stoichiometric coefficients in the balance equation, and this is divided by the concentrations of the reactants, also raised to their respective stoichiometric coefficients. Now, interestingly, the values or the magnitude of equilibrium constants can give us valuable information about the direction of equilibrium in a given reaction. Here, if K is greater than 1, the equilibrium favors the formation of the products, or it shifts to the right. If K is less than 1, the equilibrium favors the formation of the reactants, shifting to the left. Meanwhile, if it is approximately equal to 1, the concentrations of products and reactants are approximately equal at equilibrium, and so neither of them are favored at equilibrium. Here in the example, we can see that the Kc of the reaction is so much greater than 1, which is 4.56 times 10 raised to 9. And this indicates that the formation of the product is favored, or the COCl2, or cobalt-2 chloride. Next, we move on to the relationship of stoichiometry and equilibrium constants. So there are actually three cases. For the first one, as we can see here, the reaction is just reversed. And the equilibrium constant of a reaction in the reverse direction is just the inverse, or reciprocal, of the equilibrium constant of the reaction in the forward direction. For this one, it's just the reciprocal. Now for the second case, it states that the equilibrium constant of a reaction that has been multiplied by a number, which is denoted by the small letter n here, is equal to the original equilibrium constant raised to a power equal to that number. And lastly, the equilibrium constant for a net or a total reaction made up of two or more reactions is just the product of the equilibrium constants for the individual reactions. Now let us try to apply them in some examples. Here there are two given reactions as shown, and we need to get the equilibrium constant, or the Kc, of the desired chemical reaction as written below. You may pause the video to try answering. Alright, to fully understand how to solve this problem, let us break down the solution step by step. This type of problem typically requires some trial and error, wherein we just need to adjust each individual reaction to eventually arrive at or match the net reaction or the desired overall reaction. Also, this problem is an example of the third case earlier. So now for the first step, we can notice that the stoichiometric coefficients of the hydrogen fluoride and the fluoride ion in the net equation are both 2. Therefore, let us try to multiply the first equation by 2 to match the stoichiometry. And consequently, we must adjust its equilibrium constant by squaring it. Now moving on to the second step, upon observation, we can tell that the reactant here in the second equation is on the product side of the net equation, while the reverse is true for the products. Therefore, let us try to reverse the second equation to align with the net equation, and correspondingly, we must modify its equilibrium constant by taking its reciprocal. And in the final step, with both equations properly aligned, we now can cancel out the like terms similar to how we simplify equations in math. And since it is clear that we successfully performed correct operations to arrive at the net equation, we now multiply the respective Kc values to determine the equilibrium constant of the desired or the net chemical equilibrium equation or the reaction. And as a result, we get a Kc value of 0.12. Now let's try another problem about calculating equilibrium constants. Take time to read the problem first by pausing the video. So as we can see here, the problem gave the partial pressures of the H2, N2, and NH3 at equilibrium. And so for the first step, we need to set up the equation for Kp. We use Kp since the given are partial pressures. And then we raise the partial pressure of NH3 to the power of 2 because of its stoichiometric coefficient, and then divide them to the partial pressure of N2 and H2, wherein the H2 is raised to the power of 3. And again, the partial pressure of NH3 is 0.166 atm as given, 2.46 for the N2 and 7.38 for the H2. And using direct substitution, we now get a Kp value of 2.79 times 10 raised to negative 5. And we can try another problem in which not all of the equilibrium concentrations are given. Take time to read the problem by pausing the video. Alright, so this kind of problem gives initial concentrations as well as equilibrium concentration. Thus, we can utilize an ice table. For the first step, we can tabulate the concentrations, and for this problem, initial amounts of the reactants are given, so we have to input them on the corresponding I, or the initial. And also, the equilibrium concentrations of the HI is given, which is 1.87 times 10 raised to negative 3 molar. Now for the step 2, we find that the change in concentrations of AI by subtracting the initial, which is technically 0, from the equilibrium value. We get the same, which is 1.87 times 10 raised to negative 3. For step 3, we just have to relate this change in concentration of HI to the changes in the H2 and I2 concentrations using the coefficients in the balance equation. And they both have 0.935 times 10 raised to negative 3 molar concentrations. For step 4, calculate equilibrium concentrations of H2 and I2 using their initial concentrations and changes. And so in this case, just subtract them. It's just the initial minus the consumed. Going back to the ice table, we now have complete values that we can use on the calculations. And lastly, we can use the equilibrium constant expression to find the equilibrium constant value. And using just direct substitution, we get a value of 51 for the Kc. That will be all for my discussion. And just to give a summary, in this lesson, we have now learned the relationship between the magnitude of an equilibrium constant and the relative amounts of reactants and products present in an equilibrium mixture. Also, we were able to calculate an equilibrium constant from concentration measurements.
To continue the discussion, the third part will involve the application of the equilibrium constants.
In this section, we need to know that not all the reactions are in equilibrium state. So this is the reason why the reaction quotient Q exists, where it stands for any point in the reaction where equilibrium is not established. It has the same formula as Kc, except that the values for the reactant and products are again not in equilibrium. We have the general reaction where the reactants A plus B yields the products D and E. So in order to predict Q, we have to input the products in the numerator, then the products at the denominator, and all the species involved are raised to its corresponding stoichiometric coefficients. We can use Q with reference to K to predict what happens in the reaction until it reaches equilibrium. So we have this graph here where the dashed line represents the equilibrium state. So if Q is less than K, then the reaction shifts from left to right, meaning it consumes more of the reactants in order to produce more products until equilibrium is established. So if Q equals K, then the system is already in equilibrium, so no shifts are observed. Then, if Q is greater than K, then the system will shift from right to left, meaning it will consume products to produce more reactants until the equilibrium is established. So, we have a sample problem involving the use of reaction quotients. At 448 degree Celsius, the reaction where hydrogen and iodine gases are the reactants and hydrogen iodide is the product. It has an equilibrium constant value of 50.5. So predict which direction the reaction proceeds to reach equilibrium if we start with these initial concentrations in a 2-liter container. What we have to do first is to get the molar concentration by dividing the moles to total volume as shown here. So we just have to divide the total number of moles to the volume that we have. So what we now have is these values where it's already in the molar concentration. Then we just have to plug in these values in this reaction, in this formula to determine Q. Now the value for HI, that is also raised to 2, then the value for hydrogen, then iodine. So what we will be getting is 1.33, which is when you compare to K, we can see that Q is less than K. So the reaction will proceed from the reactants towards the products. So the reaction will shift from left to right. Then we also have a second example here where it involves the same reaction. So a 1-liter flask is filled with 1 mole of hydrogen gas and 2 mole of iodine gas at 448 degrees Celsius. The value of the equilibrium constant for the reaction is 50.5. What are the equilibrium concentrations of hydrogen, iodine, and hydrogen iodide in moles per liter? So what we will be doing here is we have to set up an ice table for this reaction. So I stands for the initial concentrations, then C for the changes, then E for the equilibrium. So for the initial concentrations, hydrogen has 1 molar, then iodine has 2 molar, then hydrogen iodide has 0 molar, since there's no value indicating for hydrogen iodide. Then for the changes, we have negative X for the reactants, then plus 2x for the product, since we have to take note that the stoichiometric coefficient for the product is 2, so we just have to add 2. And we need to remember that the reactants are consumed, so we are producing the product. So for the equilibrium state, we have 1 minus x, 2 minus x, then 2x. So the next step that we will be having is to determine the equilibrium constant. So we just have to input the equilibrium values in here, and we know that the equilibrium constant is 50.5. So what we do now is we just have to cross multiply these two variables in order to get this equation. Then for this one, we can note that we just have to equate it to 0. So we just have to we just have to multiply 50.5 to all these values, then transpose it to the other side of the equation in order to equate it to 0. So now we will be getting this value. Then since looking at this, we can note that this is a quadratic equation. So we can plug these values in here, where A stands for 46.5, then B stands for negative 151.5, then C equals 101. So you just have to input these values in the quadratic equation formula, or if you have a calculator, you can just use the equation part where you can set it up in the mode. Then the values will be automatically calculated for you without you needing to write this entire equation. So there will be two possible equations that we will be getting, since we have to take note of the plus and minus sign. So the answers that we will be getting are 2.323. Then the next one is we have 0.935. So if we look at this value, we can note that that this is not possible, since we should be considering the initial concentrations. So this value is greater than the initial concentrations that we have for the reactants. So the second value should be the correct answer, since if we plug this value into the equilibrium constants, we will be getting a positive value for the reactant. So knowing that, then we just reject the first answer and proceed with this one. Then we just plug this x value into the equilibrium state of the reactants and the products. So what we will be getting now is this one. So the hydrogen gas will have a concentration of 0.065 moles, molarity rather. Then for the iodine gas, we will be having 1.065 molarity. Then for the hydrogen iodide gas, we will be having 1.87 molar.
In summary, for the third part, we have been able to predict the direction of a reaction given the equilibrium constant and the concentrations of reactants and product. And we were also able to calculate equilibrium concentrations given the equilibrium constant and the starting concentrations.
Good day, everyone. So this is Edward Cantos, and let us proceed with the last section of this lesson, which is understanding Le Chatelier's principle. If a system is at dynamic equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. As the forward and reverse reactions happen simultaneously, the net concentrations of both reactants and products remain constant. Changes like reactant or product concentration causes stress on the system as the equilibrium is disturbed. For example, the equilibrium could be disturbed by either adding more of molecule B, or you could try to remove some of molecule C. According to Le Chatelier's principle, if a system at equilibrium is disturbed by a change in concentration, pressure, or temperature, the system will shift its equilibrium position so as to counter the effect of the disturbance. To further visualize this, let us consider two connected water tanks to understand a system's response to a change in concentration. So let us consider two water tanks labeled A and B. Initially, the water level in the two tanks is equal and the system is in equilibrium. Then,
Water is added to tank A. This stress raises the water level in tank A and disturbs the equilibrium. To offset this stress, some of the water flows into tank B to restore equilibrium. Conversely, if water is removed from tank B, the lowering of the water level also triggers stress. Water from tank A flows into tank B in order to restore the equilibrium. For a system at equilibrium, the reaction quotient equals the equilibrium constant. Adding more reactants to the equilibrium mixture decreases Q. According to Le Chatelier's principle, the system minimizes the stress by shifting the equilibrium position towards the products to expend the added reactant and re-establish equilibrium. Likewise, removing a product from the equilibrium mixture will lead to a similar response in order to restore equilibrium. In contrast, adding more product increases Q, thus the equilibrium position shifts towards the reactants to expend the added product and restore equilibrium. A change in concentration shifts the equilibrium position without changing the value of K. The Le Chatelier's principle can also be used to predict how a system at equilibrium would respond to the stress of a change in volume or pressure. The inverse relationship between the volume of a gas to its pressure affects the system at equilibrium. When there is a decrease in volume, an increase in pressure will occur, thereby disturbing the equilibrium. And through Le Chatelier's principle, the equilibrium will shift in a direction to minimize the stress. The ideal gas law establishes the relationship between the pressure of a gas and how this is directly proportional to the number of moles. Thus, the direction of the response to restore equilibrium is dependent on the number of moles of gas particles on either side of the reaction. As more moles of gas results in higher pressure, an increase in pressure shifts the equilibrium position towards the side with the fewer moles to lower the pressure. Likewise, a decrease in pressure shifts the equilibrium position to the side with the more moles of gas. To discuss further, let us consider a chemical equilibrium where 1 mole of gaseous phosphorus pentachloride decomposes into 1 mole of phosphorus trichloride and 1 mole of chlorine gas, a total of 2 moles of the product. If the pressure is increased, the volume of the system decreases, thereby disturbing the equilibrium, and the resulting K is lower than Q. Thus, the equilibrium position shifts towards the reactants with the fewer moles of gas particles in order to lower the pressure and restore equilibrium. Conversely, if we are to pull up the piston and increase the volume and decrease the pressure, in this case, our Q becomes smaller than our K. And in order to raise the pressure, the equilibrium position shifts towards the products and the side with the most moles of gas, and then the equilibrium is restored. Increasing the pressure by adding an inert gas to an equilibrium mixture at constant volume does not affect the equilibrium because the partial pressures of the gaseous reactants and products remain unchanged. Temperature could also affect the rate of a chemical reaction. Therefore, a change in temperature for a reaction at equilibrium acts as a stress on the system. A change in temperature changes the value of the equilibrium constant, unlike a change in concentration or volume, which shifts the equilibrium without the changing of value of K. Consider the decomposition of a gaseous phosphorus pentachloride into phosphorus trichloride and chlorine gas. For this endothermic reaction, the heat is absorbed and can be thought of as a reactant. If there is an increase in this temperature, this could be thought of as a equal of adding more of a reactant in this specific reaction. So as we added a reactant and increased its concentration, this results in an equilibrium shift towards the products, thereby producing more phosphorus trichloride and chlorine to use the extra heat that was given earlier. This is also due to the noticeable increase in the value of the equilibrium constant K. On the other hand, a decrease in temperature removes heat from the system, similar to removing a reactant. Thus, the equilibrium position shifts towards the reactants and produces more phosphorus pentachloride to release the heat because of the value of K has decreased. For an exothermic reaction, such as the gaseous reaction between sulfur dioxide and oxygen to produce sulfur trioxide, the heat released can be thought of as a product. An increase in temperature is similar to adding more of a product, and this causes the equilibrium position to shift towards the reactants, producing more sulfur dioxide and oxygen to absorb more of the added heat because of the value of K has decreased. Conversely, decreasing the temperature of the exothermic reaction removes heat, and the removal of heat is equal to the removal of a product. Thus, the equilibrium position shifts towards the products and produces more sulfur trioxide to release the heat as the K has been increased. Thus, an increase in temperature favors the products in an endothermic reaction, whereas the decrease in temperature favors the products in an exothermic reaction.
So in summary for the last part, we were able to understand how changing the concentrations, volume, or temperature of a system affects the equilibrium. And that is all for this module. Thank you very much for listening.